A rigid structure under extreme load absorbs multiple forces from different directions, all acting simultaneously on the framework. The core objective of statics is to analyze the net physical effects of these complex force systems to determine how they influence the body as a whole. Analyzing every individual intersecting and non-intersecting force in a large-scale structure is a massive analytical burden. For efficient calculation, managing dozens of independent vectors is counterproductive. Engineers solve this through mathematical reduction, condensing any complex arrangement of forces into a single equivalent force. This single equivalent force is known as the resultant. To function as a valid substitute, this resultant must precisely replicate both the translational movement and the rotational torque of the original system. The resultant serves as a mathematically precise substitute. It allows engineers to predict structural behavior by replacing multidirectional chaos with a single verifiable vector. The model begins with the simplest baseline, coplanar concurrent force systems acting on a two-dimensional plane. In a concurrent structural system, every single force's line of action passes precisely through one common central point. Because they all share a single intersection, we can identify the resultant's position simply by looking at that point. To resolve these forces into a single resultant, we use orthogonal decomposition. Using basic trigonometry, we break each individual vector into its x-axis and y-axis components. We then sum the x and y components algebraically. This reduces the entire system to just two values, the total horizontal component, Rx, and the total vertical component, Ry. These two final values form the legs of a right triangle. By applying the Pythagorean theorem, we find the final magnitude of our resultant vector, r. We then derive the exact inclination angle of the resultant by taking the inverse tangent of ry over rx. Because concurrent systems act on a single point, they govern translational movement. This allows us to focus entirely on solving for magnitude and direction. Complexity increases with non-concurrent forces, where the lines of action do not intersect at a common point. Applying forces at different structural locations induces both translational motion and a twisting rotational moment on the rigid body. To find the equivalent effect on this rectangular framework, we construct a dummy diagram. We start by replacing each original force with its x and y components, maintaining their specific points of application. To resolve the rotational effects, we apply Varignon's theorem, the principle of moments. The theorem states that the moment of the resultant must equal the algebraic sum of the moments generated by the individual forces in the system. By solving for the moment arm, d, we locate the exact line of action for the resultant relative to our origin. Non-concurrent systems can also produce a specific state known as a couple. A couple occurs when two equal, parallel, and oppositely directed forces are applied. The translational components sum to zero, but the moment sum is non-zero, resulting in a pure rotational effect. In non-concurrent systems, the point of application dictates the rotational effect. This makes position just as critical as magnitude. We can now expand this foundational logic from a two-dimensional plane into the complexity of three-dimensional spatial force systems. The mathematical logic is consistent with coplanar systems. We are simply adding a z-axis to our orthogonal decomposition. Consider these spatial parallel forces, representing gravity loads on a concrete foundation pad. Since they are vertical, we take moments about the x and z axes. This defines exact x and z coordinates for a single equivalent resultant. In full spatial non-parallel systems, force vectors move across all three dimensions simultaneously. Finding the 3D magnitude requires a single equation, the square root of the sum of the squared x, y, and z components. The final direction of the resultant in space is determined by those resulting x, y, z coordinates. Spatial force systems do not require new laws of physics. They are mastered through the rigorous application of three-dimensional orthogonal decomposition. This establishes the universal analytical workflow used to resolve any force system. Whether the system is coplanar or spatial, the engine is the same. Decompose the forces, sum the components, calculate the magnitude, and satisfy the rotational moments to define the final position. Resolving this resultant is the mandatory first step before determining if a body is in equilibrium or in motion. By condensing multi-directional forces into a single equivalent resultant, engineers translate physical chaos into a controllable mathematical model.